Hi, this is Joyce McGill. I'm in section M7 and I meet Thursdays from 3 to 6. So this is my lab 5. So basically what we're doing in this lab is we're tracking the position and velocity of a falling object and studying the effects of drag force, which is the same as air resistance, on the velocity of a falling object. So the first thing I did was I made a video of a heavy object falling. So in this case I used a marker, and the first thing I did was I made the time frame from 305 to 325. I set my calibration stick to my height because I know that I'm 5'4", so I converted that to meters and I plugged it in here, and then I set my origin on the ground where the marker lands, and the y-axis goes up and down where the marker falls, just to make it easier. So I'll go ahead and play the video real quick. So you can see the marker falling. I used tracker. I tracked the little points. And then I used that data and I plugged it into VPython. So the initial position was 2.13 meters, which you can see here on the side. Then for the initial velocity, I just took 2.096 minus 2.13 and I divided it by the time step, which is 0.033 seconds. The mass of the object is approximately 15 grams, which is the same as 0.015 kilograms. And then the time step for VPython, I used a smaller time step because the computer is able to do that. So here gravity obviously is 9.81. The gravity vector here is negative gravity times the mass of the ball. And then the net force is obviously only gravity. So here we use this equation, which is derived from the momentum principle here. It's just the velocity of the ball, the final velocity of the ball equals the initial velocity plus the net force divided by the mass times delta t. And then the position vector comes from this equation here. Final position equals initial position plus the velocity of the ball times delta t. So then I went ahead and I ran that, and it comes out like so. So I took the data from that and I used it to make my graph. So you can see here that this data is the predicted data is pretty much entirely accurate as compared to the actual data. So then for my second video for the lighter object, I just used a plastic bag, and again I set the origin where the bag hits the ground, and I used the same calibration stick for my height, and then I went ahead and tracked it. So I know that the mass of a plastic bag is approximately 4 grams, which is the same as 0.004 kilograms. So first we ran this without using drag force. So basically everything is the same as in the last one, except that we changed the mass and the initial position and velocity, which again I took from tracker here. Basically all the equations are the same. So we'll go ahead and run that, and you can see the ball move down. Okay, so using that data, here we can delete that for now. Obviously that data doesn't really work because here's the actual data and here's the predicted data. So we need to go back and add in the drag force in order for this to work properly. So we're going to go ahead and add the drag force. So what we did, the initial information is the same, but we're going to go ahead and add this component here. Basically, you have to find B, which is the constant for drag force, and you plug in this equation here, negative B times the magnitude of the ball's velocity squared times the norm of the ball's velocity. And then, because we're adding drag, we need to make sure we add that to the net force, so it'll just be the force of gravity plus the force of the drag. So we go ahead and run that. And obviously, this is the drag force arrow, and this is the gravity arrow. So that, when you add that in there, this green line here is the predicted data with drag force, and that is pretty accurate. So what does this mean? When the object, when we're comparing the velocity of the falling bag without the drag force compared to with the drag force, it appears as though the bag, or the data with the drag force, reaches a terminal velocity, and this occurs because the net force reaches 0, so the object remains at a constant velocity. The net force is 0 here because the drag force reaches a magnitude that is equal to the gravitational force. So then when we add an initial force downward to the ball, or the bag, basically we do the same thing that we did in the other runs of VPython, but you just have to add the initial force here. I just used -5 because it's a downward force, so it'll be negative, and 5 because it seemed reasonable. And when you run that, it goes a lot faster downward because this one doesn't. Let's see. So many windows. Alright. So basically, even though you add an initial force downward, it still reaches a terminal velocity because at some point the drag force reaches a magnitude that is equal to the magnitude of the gravitational force downward. So pretty much the only difference is that when you add this additional initial force, the velocity is going to be much greater, as you can see here. But the two graphs look similar, it's just shifted down. So that is the end of my lab report. That's Lab 5. Again, I'm Joyce McGill, and thank you for listening.